What we hope to do is to get you people geared up for being able to draw sketches of algebraic equations involving three unknowns. And these are the famous surfaces that you meet in your book. The book does a great job at it because he can do some shading and some traces that we can't do, but I hope to give you at least a feeling as to where those surfaces come from. The surfaces we talked about yesterday in some generality are paraboloids, hyperboloids, ellipsoids, and things of that nature. And those are the ones that you'll see most of the time in most of your applications. And as we noticed yesterday, these surfaces come from natural extensions of the plane conics. So that's why they happen to appear so much. They're fairly regular in nature. We had a couple of questions also yesterday, so let's kind of work those into the talk. On page 665, problem 8 said to sketch that particular equation. And again, I warn you that when you look at this thing, you ought to notice that this is a problem with a missing variable in 3 space. You're missing the y variable, and this falls into the classification of a function of x and z equaling a constant, and that turns out to be what we call a cylinder. Not your old right circular cylinder, but a cylindrical surface. Now xz in 2D equal 1. Just in the plane, the xz plane, you should perhaps plot a few points or realize that it's z equals 1 over x, however you want to do that. And what you'll find is that in that xz plane, you get this plane curve. And as it turns out, this is actually a hyperbola that's been rotated 45 degrees. Okay, so this is xz equals 1. For example, if x is equal to 2, then the corresponding z value is 1/2. If x equals a minus 2, the corresponding z value is a negative 1/2, etc. So you get a plot that looks something like that. Now, since the y variable is missing, and the y-axis, if you like, pierces the blackboard perpendicular to the origin, then the effect is that a point out here in 3 space directly above or in front of the blackboard also satisfies the equation because there's no restriction on the y variable. So we can let y run either positive or negative, either above or behind the blackboard. So the effect is that you're looking straight down on this cylindrical surface, and in 3 space, to try to make a sketch, you might take what we call the trace, which is what we're looking at here, the trace in the xz plane, and duplicate it as best you can over here. So here's the trace in that positive quadrant, and also down here in this negative quadrant in the xz plane. It's kind of hard to see, but as you look back along the xz plane, in that plane is this hyperbolic graph that we just drew. And I just said that you can extend your points left and right in this particular picture so that your your hyperbolic surface would look something like this. Actually, it goes in both directions, and it has 2 parts to it. Something like that. So again, that's just the right-hand part. It also goes in the left-hand part. Of course, the final effect, well, I don't know if this would be that good. The final effect is that we have a surface that opens up this way and a corresponding part that opens down this way over here, down below. So you actually have 2 sheets to your surface, and if you wanted to give it a name, I guess you'd call it a, keep getting the wrong word there, hyperbolic cylinder. Or a hyperbolic cylindrical surface. That's a mouthful. Okay, so that takes care of one of our problems. I hope. Any questions on it? Again, if you have a plain curve-looking thing, it's a cylinder of some sort in 3 space. The other problem was, I think, number 25, and that was y minus 4z squared equals 4x squared. As we do more and more of these, one is supposed to look at equations and perhaps recognize them for what they are. Notice that you have 2 variables squared and 1 to the first power. What you might want to do is write it this way: y equals 4x squared plus 4z squared. That is to combine the squares together. And as such, you might see what I indicated yesterday to be a parabolic surface, a paraboloid. If you don't see it algebraically, which is what we're supposed to get you used to, then you should go ahead and sketch it. And that's what I propose that we try to do. Knowing that it is a paraboloid, that helps because I can basically realize that the shape is there. It's just a matter of what orientation is it going to have. And that comes down to perhaps looking at the traces in the various coordinate planes. Same old story. For example, in the xz plane, that's when y equals 0. You get 0 is 4x squared plus 4z squared, and that implies that x and z both have to be equal to 0. So you get the point. We've seen this before in another situation. So in the xz plane, we get nothing but a point. And in fact, you'll notice, as we did before, that this y value is going to have to be non-negative. So everything of interest is going to be to the right of the xz plane. And here's our one point of contact in the xz plane. How about in the yz plane? This is when x equals 0. The trace you get there is y equals 4 times 0 squared. There's your x plus 4z squared. There's your parabola, y equals 4z squared in the yz plane. So you come over here and sketch a parabola. Opens up this way in that yz plane. Now you're going to have the same parabola, in fact, in the xz plane. So here in the, pardon me, is that right? Xz, yz. Okay, and the next one is the xy plane. Okay, in the xy plane, pardon me, we should also have a parabola that looks something like that. Now, again, I would not press you to try to draw the entire surface. In fact, I tend to use things in the first octant, but nonetheless, as best you can, perhaps. You might fill out the picture by actually taking another trace. For example, this might be the trace y equals 1 equals 4x squared plus 4y squared. And that would be a trace which is a circle in the plane y equals 1. In other words, it's like you're slicing bologna. You come out here at various y values, cut perpendicular, for example, at y equals 1, and those perpendicular cuts will always be these circles. Now this turns out to be, as I was talking yesterday, a paraboloid of revolution. That is, if I took this yellow curve that you see as a plane parabola and simply spun it around its axis, the y-axis here, you would develop a parabolic shape in 3 space that has these circular cross sections. So that's a very special case. If these coefficients of x and y were not equal, then you'd have elliptical cross sections and a distorted paraboloid, if you like. So that's the situation there. You might clean up your picture a bit to make it look good, or not even worry about trying to do all the octants at once. But something like that, perhaps. What you'll see in your book and what other kinds of, for example, computer programs do, would be to give you more and more traces for various levels, something like that. I can't really give you a solid performance here. But the idea is you'd have some cross-sketching, things like that, that would give you some feeling of solidity of this particular surface. I mentioned that in class, and maybe I gave you the wrong name. This is what I think I should have given you, 3D Plot Triple Star. It does this kind of a trick for you. It also goes back and kind of hides the lines. In other words, what you're not supposed to see, you don't see. It keeps track of where the various traces are. And it'll give you a fairly realistic plot very quickly, and much better than probably you or I can do together. So if you need some of these surfaces, don't forget computer graphics. It's a good way to go. Now that's pretty much the review. That was the previous section. The one I talked about yesterday more thoroughly, but not with much detail, was a section on so-called quartic surfaces, kind of a fancy name. But it comes down to looking at things that give you the rest of the conics in 3 space. That is, this was a parabola that became a paraboloid. We'd like to see what happens to ellipses and hyperbolas and what have you. So just as a sequence of examples, let's start out with an equation, x squared over, let's say, 9 plus y squared over 16 plus z squared over 4 equals 1. Again, I'm choosing things that are squares just to make life easy. Well, again, if you have the experience, if you've done your homework, let's say, you should, after a while, recognize this thing as a specific quadric surface. In fact, it's or an ellipsoid. And, in fact, it will have elliptical cross sections. Let's take a look at why that's the case. Let's take a look at the traces very quickly, I hope, in the, let's say, the xy plane. That's when z equals 0. What we get is x squared over 9 plus y squared over 16 equals 1. The z term drops out because z is held equal to 0. Of course, that's an ellipse. And you ought to be pretty good at sketching that thing after we spent a few days on conics. What kind of ellipse is it? Well, we can give you a little bit of a sketch here. Ellipses are pretty easy to sketch. X goes to plus minus 3. On the minor axis, it turns out the major axis is along the y-axis with vertices at plus minus 4. So there is that creature right there, roughly. And in the other planes, for example, the xz plane, when y equals 0, you get x squared over 9 plus z squared over 4 equals 1, another ellipse, and the same thing will happen in the yz plane. That's when x equals 0. We get y squared over 16 plus z squared over 4 equals 1. So we have similar ellipses in the 3 coordinate planes. Well, they're all different shapes. So to put them together, let's again just work in the first octant. If you've seen one of these pictures in the book, you realize that if you see the first octant, you've seen an eighth of something that looks the same all the way around. So here we are in the xy plane. There's the sketch. What I will do is take only that part that has both x and y positive. That'll be that part right there. So out here at x equals 3, we'll curve around to y equals 4, and there will be a quarter of that ellipse in that position. Okay, so we've taken care of the trace in the xy plane. In the xz plane, x goes from 3 up to z equals 2. Elliptically. And there's a quarter there, quarter of that ellipse. And in the yz plane, y goes from its 4 over there up to z equals 2. Of course, all these things need to match up. And there's 1/8 of your ellipsoid. More sections as y extends out would look something like that. And you can do the same thing in the other direction. More traces give you a better idea of what the figure looks like. And one more time, I think the book cheats a bit, plays a little unfair because they get to use shading there, and so you get to see these dark edges as they roll past you into the distance. I don't know if that's really playing the game quite correctly. But nonetheless, with a little bit more effort, or with a computer program like 3D Plot Triple Star, by now I don't think you can see it as well, but you're supposed to get a better feeling of that shape. Okay, so that's the ellipsoid. Ellipses in all cross sections, in fact, all traces. Any questions? That's probably the easiest one to spot. The key is that each of the variables appears as only a square, and if you can put it in this form, you get nothing but pluses all the way across. While I'm thinking of it, of course, you can take these ellipsoids and translate them, if you wish, x minus h quantity squared, y minus k quantity squared, z minus l quantity squared would move the center of the ellipsoid off to h, k, and l. And you can also rotate this stuff in 3 space. If you ever have the time or the opportunity, you ought to go over to the engineering department. They have some new workstations that do 3-dimensional projective pictures on a screen, on a video screen, and in real time, by just twisting knobs, you can get this thing to rotate in any direction you wish. You actually take a look at the thing, and it actually spins there before your very eyes. It's done with, actually, it's not done with a computer at that point. It's done by hardwire within the video screen itself, or the monitor. So that's why it's instantaneous. It's like driving the thing. Okay, so what happens if you throw in one negative sign? That's what we talked about yesterday. Let's put in a big negative right there. Anyone happen to remember what I told you what that is? Well, by the fact that no one's answered, maybe it's a good thing we're going to sketch it. I think it's this. We'll check it when I sketch it out, but it should be a hyperboloid with either 1 or 2 negative signs in there. That's the difference. Let's see. If you don't believe me, and I'm not ever sure myself, being a skeptic, we got to go ahead and see what's going on here. So let's do our traces again. XY plane, z equals 0. We've got, well, actually we've got the same thing. We still have an ellipse. It's the same ellipse that we have there already. Hope something changes. It will, of course. In the xz plane, when y equals 0, we have maybe you can help me on that one. That's old stuff. Hyperbola. And of course, that's where the name comes from. So there's the difference. We have now changed to a hyperbola from an ellipse. And the same thing will be true in the yz plane. when x equals 0, you'll have y squared over 16 minus the z squared over 4 equals 1, another hyperbola. So the only thing that stays the same is this green curve down here. Let's start all over then. Let's try to take a look at maybe a little bit more complete picture. The ellipse in the xy plane, as I said before, was that green thing. Starts here at 3 and goes over here to 4. Something like that. So there's your x squared over 9 plus y squared over 16 equals 1. That's the trace in the xy plane. That was the same. Now this is a hyperbola in the xz plane. Let's do a little bit of a sketch right here. Xz plane, that hyperbola will have x-intercepts at plus minus 3, no z-intercepts, and of course that's the typical situation that we've seen many times in the book, hyperbola looking like this, opening up on the x-axis with vertices at x equals plus minus 3. So let me try to include a little bit of that information in our sketch here. Let's make this red in the xz plane so that it's a little bit tough, but coming up above you down to 3 and then down below you is that branch right there. And the other branch is back there in the other half of the xz plane. And let's just do a very light picture, maybe look something like that, back down there. That's back in the back, kind of keep it light so we don't get too involved with that. How about the other hyperbola? That's in the yz plane, and that intersects the y-axis at plus minus 4. So we will have over here something like that, and also something similar over there. Okay, that didn't show up too well. Let's do that a little bit more darkly. So at least we have the minimums. We have the xy plane intercept trace as an ellipse. Here we have one branch of a hyperbola in this xz plane and another branch over here of another hyperbola in the yz plane. And the other branch is back in the background somewhere. Now that may not be enough for you. What you also might do is throw in some other traces. The one that might be of interest is, for example, let's let z equal 1. Let's see what that trace would look like. If you put z equals 1 in here, let's make it 2. The numbers are better. If I put a z equal 2 in here, z squared over 4 will be 1. Add it to the other side, I'll get x squared over 9 plus y squared over 16 equals a 2, and not just a 1 as we had here. So if I go up 2 units on the z-axis, turns out that I get, again, another ellipse. It's going to look something like that. And if you took more and more of these horizontal traces, you'd see all of these ellipses stacked one on top of the other. In fact, there'd be one, let's say down here at z equals minus 2. This was z equals plus 2 up here. I don't know how well I'm doing, but the idea, let me again, step back and give you kind of a freehand sketch, the idea is that you have a shape that looks like this. It might be familiar. Here are those ellipses we were talking about this way, hyperbolic this way. Might look familiar. That's supposed to look something like a cooling tower. It's roughly the shape that they use. And the reason they use it, the engineers tell me, is it has a very strong, it is a very strong structure because of its geometric properties. So those things do occur out there. I don't know if it's in nature. Not sure what the status of atomic power plants are these days. Maybe they're unnatural. But anyway, that's the shape that you're supposed to look at. And this is a hyperboloid of one sheet, meaning that if you had a nice thin sheet of rubber, let's say, you could wrap it around itself and bend it in, and you've got the entire surface, basically. And the reason for a specification of one sheet has to do with the fact that there is exactly one negative sign there. If there were two, then you'd have two sheets, and actually the picture is quite a bit different. It's also very difficult to draw. I think the safest thing I could do would be to refer you to your book where there is a fairly decent picture. But to give you at least an idea, since maybe you don't have your book here, let me try to give you a freehand sketch of that as well. The two-sheeted hyperboloid kind of has a bullet shape pointing another bullet shape back here. It's kind of hard because I'm looking at the thing from the back. But here comes, in this case, the x-axis, pierces through this, hits this bullet shape, and again pierces through it back there. What happened was, let me refresh your memory, if one takes a hyperbola, like this purple one here, and spins it around the z-axis, you get this one-sheeted hyperboloid. If you take both branches of that purple hyperbola and spin it around the y-axis, you get a shape like this one over here, a two-sheeted affair. And that's about as good as I can do usually. You can look at it on edge. There are your two hyperbolas, so to speak, the two bullet shapes, with the spinning done, I guess in this case, around the x-axis. This is where shading in your book really comes in handy, no doubt about it. Well, that's not a real good job, but there is a difference between two hyperboloids. Fundamentally, they are very different looking shapes, but they still fall into the same classification. Okay, let's take off and look at yet another surface. Let's get rid of the double negatives and put a 0 on that side. Actually, you might say, why 0? Why don't you put a 2 or something? Notice if there's any non-zero value here, you can divide through by that number and absorb it into these denominators. So this classic situation is either you've made it into a standard form with a 1, or if you can't, it's got to be a 0 sitting there. So what happens if you have that situation? Again, let's take a look at your traces. XY plane seems to be a good place to start. What do you know? One more time, we get the same old ellipse. Same green picture over there, I guess. Is that true? No, we don't. Fooled myself. We do not get the same green picture because we changed it to a 0. What's that going to be? It's kind of like the paraboloid. There's only one point, the origin. X equals z equals 0 too, I guess. X equals y equals 0 in z equals 0 plane, so that's the origin. Not too exciting. Maybe we get something better in the xz plane. Set y equals 0. We get x squared over 9 minus z squared over 4 equals 0. What's that? that's something you probably haven't seen too much recently. It's a lot easier than you think. We could say that this is z squared over 4 equals x squared over 9. Take square roots of both sides. Z over 2 is plus minus x over 3, or z is plus minus 2/3 x. So what's that? Z equals 2/3 x in a plane. This is a pair of lines, two intersecting lines. And you're going to find that that's the same situation in the YZ plane as well. If you said x equals 0, you've got y squared over 16 minus z squared over 4 equals 0. If you solve that, I think you'll see that z is plus minus 2/4, 1/2, well, 2/4 times y. And that's also a pair of lines. Let's graph this one. In the YZ plane, you've got z equals plus 1/2 y and also minus 1/2 y. Looks like that. So let's concentrate on first octant again, so the picture won't be too complicated. We just said that in the YZ plane, you get this one part of the line anyway, y equals 1/2 z. That would be coming up off in this direction. And of course that extends down in the other direction as well. And off in this direction you get z equals minus 1/2 y. Let's kind of put that on hold for a second, see if we really need it. The other plane, the XZ plane, in the first octant would involve only z equals 2/3 x. That extends down below as well, and there's a corresponding second line out of our region as well. So down the XZ plane, here comes this line. Out there in the YZ plane, up goes that line. This point was discovered, but that's not too exciting. In the XY plane, let's see what happens if you look at yet another trace. Let's see what happens if you say cut it at z equals 2 again. If z equals 2, you get x squared over 9 plus y squared over 16 equals 0 plus z squared over 4, or 1. So at z equals 2, in that plane, you get an ellipse. Trying to give you a feeling for that ellipse. Up here, when z equals 2, the ellipse curves around something like that. And for other values of z, you would see corresponding traces like that. And that's also duplicated down below. Just looking at that, can you think of a good name for it? Please be easy on me. It's my picture, I realize, but it's a cone. You speak of it as being one cone with an upper and a lower nap. I haven't given you the lower nap, nor have I shown you everything else. But if you look at these cross sections, notice that you have these elliptical traces this way, but you have straight lines, as it turns out, as you go around this way. I'm actually putting in more than I should, but something like that would be the case. So this turns out to be, this equation right here, turns out to be a cone. And in particular, it's not circular, but elliptic. You might say, well, where does this fit into the scheme of conic sections? We took a parabola, spun it, got a paraboloid, took an ellipse, spun it, got an ellipsoid, got the hyperboloid. Where do you get cones from? Well, let me just make it up. You can, of course, talk about hyperbolas, and if you do, you tend to talk about their asymptotes as well. So in fact, cones very naturally go together with hyperbolas. As you spin, let's say, this hyperbola around the y-axis, you get hyperboloids of 2 sheet nestled within a cone. And when you come into Calculus 3, you will in fact be looking at some situations where that's a natural relationship. Hyperboloids somehow related to cones through their asymptotes. Okay, I think we only got a couple more to do. I think we can do them pretty quickly. Let's now drop the second power and make that into a first power. Anybody have an idea of what that is before we get going? Paraboloid. I was hoping somebody would come up with that. That was the one I told you about at the very top of the class. 2 squared terms, 1 linear term, and you can solve for the linear terms of the squares, basically. That's what I look for. So we've done that. Let's skip over that one. Now let's throw in our second negative sign, and that one we haven't looked at least on the blackboard yet. And this turns out to be the hyperbolic paraboloid, or the saddle surface. Let's take a look at the traces and see what we can do. Turns out usually not too much. XY plane. X squared over 9 minus y squared over 16 equals 0. Sound familiar? Should. What is it? Pair of lines. Y is plus minus 4/3 x. Pair of lines there. XZ plane. Let y be 0. You get x squared over 9 minus z over 4 equals 0. What's that? Parabola. And it turns out you get the same thing in the YZ plane. Okay, you get another parabola. Let me put those together as best I can. Okay, xy plane, y equals plus minus 4/3 x. That'll be something that comes out maybe like this. That's part of it. XZ plane. Let me make a sketch of that one. XZ plane is z is 4/9 x squared. And since I'm trying to get stuck in the first octant, we'll take this portion right here. And that's in the XZ plane, so that'll be coming up towards us something like that. And continuing on in the back, maybe lightly, just for reference. Now, in the YZ plane, the picture's different. If you solve here, it's going to be z is a negative 4/16 y squared. And that means we're going to have a picture that goes down below. Z is a minus 4/16 y squared. Let me put this one in white, indicate that what I will show will only be in the yellow, and that'll be over here. Again with a corresponding part here. Now I think at this point I got to stop. Not because there isn't more to do, there certainly is, but I don't think I can do it. I can't give you really good sketches at this point. But what you're supposed to be seeing here, as I said by this particular name, is a saddle surface. In a sense, if you're sitting in the saddle, that might be the horn of the saddle, and that's the back of it. Your legs would drape over the yellow part. And so what you have is a surface that's kind of opening up this way, but simultaneously in the other direction opening down this way. It's very difficult to draw. If you had the computer, you could see a fairly good sketch. I keep pulling it out every day. Why don't I do it one more time? There it is. That's your saddle surface. And there you can see the opening parabola on the one, what do we have here, YZ plane. The plane coming out at you is the parabola opening downward. I guess we have it backwards from the picture you see here. And what you don't see are the horizontal cross sections. Those turn out to be the hyperbolas. And the pair of lines, it's kind of hard to, they're not here of course, but they start at the origin and move out at an equal zero altitude along the saddle. That is, you can look across the saddle and see those lines as points, as traces in those particular directions. It's really a tough one to come up with a decent picture of. Again, your book does a good job with shading, of course. It also has a fancier name. It's called a hyperbolic paraboloid because it does have these parabolic shapes, but with hyperbolic cross sections horizontally. If you want to try to draw it, good luck. That pretty much, I think, ends the story. In future discussions in Calc 2, we may not do much more, but in Calc 3 in particular, when you talk about surfaces and volumes and things of that nature, you will find that you will almost always come back to cylinders, paraboloids, ellipsoids, hyperboloids, cones, and maybe a saddle surface or two just to keep life exciting. So get used to looking at the equations. In fact, I realize you've got a few problems to do. I hope you can sit down and make a decent sketch of them. I've had years of practice. I'm not getting any better. But what I would suggest you do is at least go through the odd problems, look at the equation, and maybe with a little algebraic manipulation say, aha, I know what that is. That's a hyperboloid of two sheets. Maybe you can't draw it, but at least you can experience the thrill of recognizing what the thing is before you even try to draw it. You know, if I recognize a saddle surface, I know I don't even want to draw it. That's a little bit of a start for me. So really go through all the odd problems if you can and try to recognize what they are, and once in a while throw in a quick sketch to see if you can do it.